All right, welcome everyone to Satisfying Software. Today I have with me Barry O'Reilly, founder of Black Tulip and inventor of Residue Theory, and the author of two books right now, Residues and the Architect's Paradox. Welcome, Barry.
Thank you. Okay.
So to start off, a few weeks ago, I read a blog post from you on LinkedIn, and it says that, as an industry, software development, we are mostly lost. Could you extend on that a bit?
Yes, I can't remember what blog post that was. It sounds like all of them. So I think that there is a lostness to us in terms of who are we, what do we believe in, where do we come from, why do we think the things we think? And our industry is very, very young compared to a lot of other people, a lot of other industries. And we haven't really found ourselves yet. And what happened, and if this is in the new book, you'll find this history trace. We had this very mathematical beginning, which started, the story can start with Turing and von Neumann, and then we move through Dijkstra. Somewhere in the 60s, we kind of lose contact with mathematics and we start to have conjecture. And we start to have people say, I think everything's made of objects, or I think everything's made of services, and the mathematics is gone at this point. And it starts to be a case of what do we believe in? And a few generations of software engineers talk about these things, write about these things, and there becomes a sort of accepted way of talking about them. And we get terms like coupling and coherence, which everyone uses, but when you push a developer to really define it, it's really, really tough. And the end result of this is that when you could take a software engineer and say, look, I'm looking at your architecture, I'm looking at the design you've made, there's three components here.
Hmm.
Why three? Why not two? Why not four? And what will happen, and there's research to show this, what will happen is that people will not be able to justify their architectural decisions because they're not quite sure where they've come from. They come from a gut feeling we build up over the course of a career. And that gut feeling is something, it's all we've got, but it's something we can rely on. Right? We get it right, some of us, quite a lot. And the the issue is then we are a little bit lost when we ask, who are you? How did you arrive at this set of decisions? If you ask a building architect, why is there three beams here, not four, not two? If they can't answer that question, there's a very good chance that they're going to go to prison. For us, nobody cares. and, and and that's what I mean by lost. We don't quite know who we are. And to figure out who we are requires sort of scraping at the surface of our ideas. Where did this come from? Why do I believe this? Why do I think this? It's an incredibly difficult journey for software engineers because for most people, the reaction to this kind of thinking is, will you just be quiet? Look, things are sort of working. Don't rock the boat, okay? Don't expose us. Because we don't know why we think the way we think. We don't know where ideas come from. And I find that exploration tremendously interesting and exciting. A lot of people wish I would be quiet and just get on with it. Like, just take the patterns, take the ideas from the past. Don't ask too many questions, execute. And that keeps us lost.
So is that sort of how you got into residuality, saying that I want something more than to be lost?
Yes. So how I invented residuality was I was flown to head office and they said, look, we have a problem. We don't have enough architects for this new world. And the new world was a world of cloud and distributed systems instead of these massive on-prem platforms that we were used to. How do we teach architects? And they said, we need you to teach a bunch of architects, tons of them. We need tons of architects, hundreds. And I said, okay, fair enough. What do you want me to teach them? And they said, we want you to teach them to do exactly whatever it is that you do, because that works. And then I had to leave that office feeling very, very nervous because as soon as they said that, I realized that I have no idea how I do what I do. I have no idea why I do what I do. I know that I have a bunch of instincts, which I've honed over time, that I can trust. I trust my own instinct when it comes to the design of software systems, and they, um, There we go. And those ideas I can trust, but how can I describe that in a way that's concrete and concrete enough to teach to someone else? And so I had to go off and dig in my own thoughts for a very long time, and figure out, well, what do I do? And I started watching what I did. I started watching what other senior architects did, and I came to the conclusion that the difference between the people who could really do this, and the people who would struggle with it, was your relationship to uncertainty. How comfortable were you whenever things were uncertain? When you ask a question and say, well, what is a customer to you? And your your business people are able to describe that and tell you all the different kinds of customers. Most people can deal with that situation, but a situation where it's very obvious after a few minutes of waffling that your business doesn't know who their customers are, hasn't really thought about this problem, that was where the senior architect could kick in and work with that uncertainty. So I started to dig into, well, who knows anything about uncertainty?
Yeah.
And then, so firstly, I went to I'm a mathematician, so I went to mathematics, I went to Bayes, I went to all the stuff that it's done there, probability, and eventually found my way through, through Nassim Taleb, into the complexity sciences proper. And so Prigogine and Kaufman and all of that stuff. And from there, then I started to develop ideas around, this is what's actually happening. What I'm doing all the time as an architect is I'm not designing something. I'm not taking facts from the world and turning those facts into code. I'm actually thinking about where is the uncertainty? Where is it going to push this structure? Where is it going to force my code to go? Which is this sort of upside down way of thinking about architecture. And once I was able to articulate that, which was crude at the start, then I was able to teach it, and it became much, much easier. And then what happened was that I left my employer, left big tech and went out on my own because I had a family and the two things just weren't. So kids came along, it just wasn't going to work anymore. And I went out on my own, and lots of people kept saying, "Hey, will you come and talk about that thing you were talking about before?" And as I noticed that people were interested in it. And then I went to DDD Europe in 2019 and talked about some of these ideas in their raw form, um, and got a lot more interest because of that. And at that point, I had a decision to make. I said, do I want to be this tech person who goes around conferences, talks about these ideas and things? And I thought, I don't really want to do that. I want to do something different. So I went back to university. I said, I'm going to take these ideas and I'm going to destroy them. I'm going to destroy my own ideas. Either at the end of this process, they'll be standing up and they'll be real, or I'll have found out why they're wrong, rather than, just go around promoting another bunch of ideas, to confuse people even more that weren't proven. And that's when, in that process of doing a PhD, I was forced to really articulate things, which is where the idea of residues came in as a better way of describing what I've been saying. And that's where the ideas were born, and then given a little bit of scientific weight behind them as well. So that's the sort of origin story of residuality, is that I had no idea, like most people in the industry, of what I actually did or why I did it.
Yeah, I understand that. Like, I have a hobby of decision-making theory. Which mostly, like in economics, they teach you how to make good decisions. And this concept of any decision you make, you do with a level of uncertainty. You do it under uncertainty. So your outcome might never be what you want, because
Yeah,
the level of uncertainty always, it depends. If I
exactly.
uh, if I make an easy decision, if I'm coding or something, if I need to implement a feature, how uncertain I am about that I'm delivering the right thing is okay. But when it comes to architecture, I always say, like, the level of uncertainty is quite high because you can't predict the future. And also you don't have at any given point all the knowledge to actually make a good decision. So your uncertainty in a design decision, architecture decision is quite high there. Um, but that doesn't mean you didn't make a good decision. Eh? So the quality of my
Yeah.
decision is something different than the quality of my outcome. And my architecture is the outcome and might not live up to the expectations. Eh? But residuality theory, if I understood it correctly, it sort of tries to say that you try to create a system that no matter what the future is, will actually be able to handle that future?
Yeah, well, we can never make that promise. That would be too good. So there's always in the systems we work with, which is business systems. Uh, there is a complexity. There's just like you describe. It's impossible to know the outcomes of your decisions. It's impossible to know if it's a good decision really until it executes. And there's a bunch of different strategies we can use as software people to cope with that. And the original strategy was to bury our heads in the sand and say, look, we do the technical stuff. We don't care about all of this fluff and woo-woo and business people and emotions and customers and all of that. We just write code. It either runs or it doesn't. And everything else is your problem. And then it became obvious, moving into the 1980s, I guess, that this isn't going to cut it anymore. And we started to try and take responsibility for how the software changed and moved. And I guess with Dijkstra in 68. And so that that means that decision making in the environment is very, very important to us, because it's going to break our software. It's going to constantly cause it to crack. And residuality is giving us a way to build software for the conditions where we don't know what's going to happen. Whereas the engineering paradigm, which we live on today, which comes from the late 60s, the idea that software is an engineering discipline, is that we can gather all the information about an environment and we can be certain about it. And that's because it comes from physics, it comes from mechanical systems where you can know everything about the environment, more or less. And so we took the tools from these disciplines of certainty into a discipline of uncertainty. And then what happens is that we can build something using those tools and say, the tools say it's right. I've tested it according to my specification. I've analyzed language according to the tools I've been given, so it must be right. And then we put it into production and all hell breaks loose. So we say, well, why is this happening again? And we never know. And so we blame our stakeholders. You didn't tell us the right things. So it must be your fault. Residues is a way to protect us against that by being very, very negative from the outset and saying, look, whatever decision you make, it's wrong. There's something out there that you don't know about. There's going to be a shift, a movement in the environment, and it's going to cause your architecture to crack. And so instead of focusing on what's out there and how do we describe it ever more accurately, we give up on that and we say, let's look at the architecture and describe where it cracks. When something moves, where does it break? Where are the crumble zones? Where are the parts when it cracks here that's dangerous? And by focusing on those cracks and changing the architecture so that it cracks in a very specific way, it gives us something called criticality, which is what happens when an architecture is exposed to something that wasn't in the spec, as I call it, off-spec architecture. When it's exposed to something that wasn't there from the beginning, but it still holds up more or less, then that's when we've got to this point of criticality. And the nice thing about the ideas that I've drawn up now is that you can actually show mathematically that this is happening as you move through your architectural process. And so we're bringing what we do back to something mathematical which we lost touch with in 60, 68, 66 kind of thing.
Yeah. So we talk about criticality, and you said, we need to find the cracks. And you mentioned that you find the cracks by putting stressors on the system. Could you give a few examples of the stressors that you would put on a software system to see where it cracks?
Yeah, so this is how we find the cracks in a system. We stress it from the environment. We say what could happen, and then we trace that happening down to this. Well, if this happened, the architecture would break here. The really obvious ones that people will find really easy and intuitive is things like what happens if a disk crashes or the network goes down or there's a power outage, all of those technical things. But we need to get beyond that. And I start to ask things like, what happens if a competitor drops their price? And that will cause a shift in the business environment. It will cause all kinds of shifts among competitors and employees and business processes. And eventually, when you boil it down, somewhere your code structure is going to have to shift. And then we say, where does it shift? Where's the vulnerability? What about that shift is awkward or difficult to fix? What have we not covered here? And the reason I use that example is to try and get architects and developers used to thinking in business terms, because that's not the easiest thing in the world for them. And I think that, for example, domain-driven design in that case is a fantastic way to get people to developers to engage with the world outside of their code. Um, and so the act of modeling a business automatically forces you into that kind of sphere. But one of the things that I then encourage as well is this idea of randomness. Is that random words, random ideas, random things can be used to stress your architecture, even if they have nothing to do with what's actually what you think is going to happen. By having these random discussions about, well, okay, just look at a newspaper. What's happening in the world today? There's a person over here in a different country making some strange decisions. Is that going to affect my architecture in some way? And learning how to figure out, well, how is this going to hit my market? How is this going to hit our business? How would this turn up in the architecture? And by getting good at that kind of thing, you get much, much better at understanding where your architecture is going to crack. And so these stressors require, firstly, an understanding of your business domain, which is something that a lot of devs struggle understanding that we need to do this. But another thing it does is it doesn't allow you to drift off into that ivory tower where you just talk about business problems. You have to keep it related to the tech and the structure, which is a much more demanding kind of architecture. So I got a little bit of pushback in the beginning from sort of old school enterprise architects who had drifted off from the technology, and they didn't like that I was telling them that you have to get back out, you have to get your hands dirty, right? You have to know how this stuff works and how your decisions are actually affecting it. And so stressing is learning how to stress is kind of a shortcut to the kind of knowledge that an architect after 25 years in the industry is going to have that. And one of the things that's come out of the work I've done in the last couple of years is when I have veteran architects in my workshops, is that they tend to say, this is what we do. This is where you end up after a certain amount of time in the industry. We don't have all these fancy words for it, they usually say, but this is what we do. It's repeated stressing from the environment and focusing on where that stress touches your structure. And that allows you to be quite abstract. So you don't have to identify exactly what's going to happen in the future. Your stressors can be silly. They can be far removed from what the business would see as realistic. And it turns out there's a mathematical explanation for why you can use a bunch of stressors that are considered to be completely unrealistic or ridiculous even, and still get a better result than someone who's patiently gathering real requirements with evidence for them. It's a much, much faster process and a much more fun process. One of the things I set out to achieve with all of this was to make architecture fun again, because there's a whole generation of developers who think that architects are boring old people who turn up with lines and boxes and say, you have to do it like this. You're not allowed to have fun. Work should be boring. It should follow this process. It should always look the same. And there's a disconnect I found between younger developers and the old school architects. And this is a way for those younger developers to do everything that an architect does, but without conforming to that old school, that sort of tragically stiff way of looking at the world that you'll find.
Yeah. Well, I still think architecture is fun. Maybe I'm not old school. I never really was. One question I have about the stressors, though, is that so one thing I noticed, when I'm looking at architectures with different companies, is that there's this habit of over designing, over architecting. So how do stressors prevent from then actually going into over design?
Yeah. So this is a common worry that people have when you start talking about, well, we're going to take any stressor, something that might not happen, and we're going to build that into our system. And this seems to be something, the way people talk about this is like a deep-seated trauma in the industry. So developers start saying, oh, you don't want to over-engineer, you don't want to gold plate everything. Um, so Residuality actually pushes back against that. And you'll see in the book, when I talk about criticality, there's two mistakes you can make when it comes to criticality. One is that your system can have too few components and too few links between those components that makes the system incredibly vulnerable. And that means that you're far, far away from what we call the edge of chaos, where or a level of criticality that's good for a system, and you have to break that system up a little bit in order to allow it to survive in off spec. On the other hand, you can go all the way out. You can have too many components, too much happening, too many links, and in complexity science terms, it massively increases the number of attractors, and it means that what happens is that the system becomes incredibly difficult to manage. From an operations perspective, it becomes an absolute nightmare. And in residuality, that's something that can be stressed. And so when you stress a system that's gone too far, and has too many components, too many structures, too many ideas in it, you start to realize that this is going to cause us problems. And residuality will actually take an over-engineered system and push it back towards something much more sensible. But I'd have to add to that my consultancy career is almost 100% concerned with rescuing crashed projects. And in those crashed projects, I very, very rarely see over-engineered solutions. What I see is, as I say in the book, under-engineered solutions where people haven't spent enough time stressing. They put the thing into production and it gets stressed by its own environment and it collapses. Over-engineering is something I seen a lot more of when I was younger. And I guess all my colleagues were younger as well, and we didn't know what we were doing, and we got excited about things like dependency injection, and we did silly things. And I never personally did it, but I know a lot of people who lost a lot of months of their lives to persistence layers and things like that. And there's a fear of over engineering, which I think I don't see so much of in modern cloud platforms these days. It's much more the other way with under engineering, but residuality will help you work against both. And the important thing about residues is that you're exposing the cracks in your architecture. You haven't actually built anything yet while you're doing this, so you don't have to implement absolutely everything. And the idea is that what residuality does is rather than designing an architecture, it trains an architecture like a machine learning model. And it will train the architecture away from monolithic structures if that's what the business environment demands, and away from these over-engineered, over-designed architectures as well. So it will help you find that point of criticality. And if you overshoot and do something stupid, then the numbers actually tell you that, yeah, you shouldn't have done this. You should not have put this thing in here. It's gotten worse because of you. So it's very hard to hide the truth from these methods.
Yeah.
So
So you define a residue as what is left over after you put stressors on the system, right?
yeah,
Um, what took me a while to understand, and maybe it's because of the word leftover, but it's not only to subtract from the software system, it's also to add additions. You're saying that, okay, this is too big, we need to split this up. That's correct, right?
yeah. So the way we think about it is, I have a system with a little design in my head, which I call a naive architecture, and and that's my first sort of sketch. That's what I get to. And then I imagine this stressor, and I say, what would happen to my architecture in this stressor? And you look at it and you say, well, half the components are gone. Some of them are on fire. Some of them are working, but they're not working properly anymore. This is my residue. And then you ask yourself, am I happy with this? And you say, no, I'm absolutely not happy with this. So what would I do to this residue? What would I do to this naive architecture to give me a different residue? So you go in and you add a component, or maybe you split a component, or maybe you put a few components together and make it smaller because you've increased your attack surface or something. And then you rerun the idea. You say, if the stressor now hits this new augmented um, architecture and it collapses again, am I happier with what's left over? Am I happier with what's there? And you'll say, yes, I fixed it. This is a much better way to collapse than we had before. But there's a difference. There's a delta between those two residues. And that delta I refer to, that becomes part of your new residue. That delta is then part of the residue. And so you have a residue before the stressor, a residue after the stressor. And what you're really interested in is the delta between the two. What did I change in the original architecture to make that? And then you can say that an architecture is built up of all these residues because you're going to have hundreds of them. And so the residue becomes this little building block, which is very different than any building block we've had before. And it's nicely agnostic. It doesn't, so you can do this with services or object or functions or whatever you're working with. It doesn't have to be it's not religious about any of that, any of those kind of things. And then you can express your architecture as a series of these residues. There are many people have suggested that shouldn't you give the original residue and the new residue a different name because that's confusing. So you're not alone in finding that confusing. But I was trying to be I was trying to have fewer concepts in the whole thing because there's quite a lot of them. It is I usually say to people that the ideas in residuality, because we sort of slowly looking into making this a university course, and it's going to be an entire university term to get these ideas into people's heads. So it's as big as object orientation in terms of the conceptual noise inside it. And so most people have learned residuality from a 45-minute video, maybe, and then read the book. And that's it's going to take a bit more than that. What we find is that when we go through the 3-day workshop, people actually build something during those 3 days, and by the end of the 3 days, it's like, that's how it works. And at some point, we might be able to just teach the mechanism. It's like first you stress it, then you write this down in this column of this spreadsheet, then you put them all together, and then you have an architecture, and people will be able to work without actually knowing all the ins and outs and why it actually works and relating it back to network science and complexity science to say that there's an actual mathematical reason why we do this in this particular way. But for the minute, because the idea is so new, we have to justify everything at the science level, at the philosophy level, to show that this is real, this is built on something. It's not just something some person dreamed up to make it sound cool when we built it. It does sound cool, but that wasn't the purpose. It was there are layers and layers to this, and as time goes on and these ideas become more and more accepted, then I think we'll find developers who are happy just to execute on the ideas without having to go deep in and understand why it actually works. It's just everyone else says it works, let's just do it. Um, but I think we're way away from that yet.
Yes, and I think for some of the things we have in our industry, like some of the solid and the dry, and they're just mindlessly following the principles. I'm not sure that they should mindlessly follow
Exactly. Yeah.
anything. Anyways, yes. So you said that doing all of this is very easy. You have two phases: the stressor analysis, where you put all the stressors and see how the system needs to change to somewhat survive it. And then you have the contagion analysis, which is looking at the connections between the components, right?
So contagion analysis is a way of questioning our decomposition. So once you've done the stressor analysis, you've got all these residues, and you've got all these little deltas as well, which is the interesting part of the residue. And what you want to do then is integrate all of these, or as many of these as is politically acceptable, into a single architecture. And you've got to make sure then, because one of the things we talk about is these are complex systems, and as you add more components to a complex system, you're constantly changing its behavior, and you might screw it up while you're adding those things. And so what we want to do is test that. And what we do is we create a network, and that network shows the relationships between these stressors in the business environment and the components that you've come up with. And those components can come from anywhere, right? So they can be whatever way you like or love to decompose a system. And we put them into a matrix, and that gives us an enormous amount of benefits. Firstly, it allows us to write everything down in a concrete way that we can see it. So your average software architect has to carry all this in their head. It's a very fragile structure, I find. If I try to carry an entire architecture in my head, which you have to do while you're designing it, easily crumble like a Jenga if someone asks the wrong question at the wrong time and then you miss details. It's tough to communicate things. The matrix allows us to, in black and white, say, this is what we've done. This is how all these things are connected to each other. And it allows us to catch um, what I call invisible or hyperliminal coupling between our components, because sometimes we don't see that things are connected, and you'll only see that two things are connected in production when it crashes in it, when there's a very specific kind of stress or change in the environment. And the matrix allows us to catch that. It allows us to then figure out where is the coupling in this application. And that usually is a surprise because we have a picture in our head of what's coupled, but when we write it down, everyone goes, "Ooh, who would have thought that?" And so this allows us to have a much more honest conversation, because I find coupling one of those terms that can mean so many things. And it means different things to every architect who uses the term. And there's some really excellent definitions of coupling out there recently from Vlad. Um, but to get everyone to that level of understanding of coupling is very, very difficult. So what I like to do is to make it really, really explicit with numbers that these things are coupled and we don't know why. And the next thing that happens that comes out of this, it allows you to see where your system is vulnerable, where it's too coupled. It allows you to see where it's not coupled, which is also a kind of weirdness that sometimes shows up. And it allows you to then, through the matrix, and you can actually write some little algorithms to figure these things out, but normally you don't need to do that. You can start to talk about cohesion in a completely different way, in a way that's mathematical, because cohesion is a feeling. And feelings in engineering have a weird relationship to each other. So we try to separate them as much as we can, so at least that we can express our feelings mathematically. And and so you get this idea of cohesion. You get to see which components or which functions actually should get to live together. Now, some of the ideas in that matrix, I was inspired by. I took a course in systems engineering at MIT, and the way that they make component decisions for aeroplanes at Boeing and for spaceships at NASA is through these things called design structure uh, um, matrices, where they use matrices to make sure that we're not forgetting all of the relationships that these components have to each other, and we can find clusters of components that live and die together, and that's the cohesion that I talk about. Isn't conceptual cohesion where we say that all of these things are about billing, so they should all be in the component called billing. That gets us into trouble. With Parnas told us in 71 not to do that. Whereas the cohesion that I'm looking for is cohesion under stress, which components live and die together, and that falls out of these matrices, and it gives us a very nice way of documenting our architectures, of questioning our architectures, and of gathering a bunch of architects and developers around a single system, and getting all the heat out of the discussion and saying, look, what is it you're trying to say? Show me in ones and zeros on this matrix what it is that you're scared of. And if you can't put it in ones and zeros, then you might just be having emotions today. So let's move on. And it allows teams to assemble around something that's and just the matrices is one of those things that's incredibly simple, where if people just adopted the practice, it would be incredibly easy to do.
Yeah.
But obviously people won't just adopt a practice, or shouldn't just adopt a practice because I say so. That would be really weird. And so there's a lot of math behind why this actually works, and some empirical proof as to why it actually works as well. But it makes things much, much more concrete. And so you can read through the book Residues, and especially through the Architect's Paradox, and you'll see that what's actually happening is it's a war on fluffiness. I'm trying to get rid of words that don't have any meaning, or words that have lots and lots of different meanings that can be interpreted in different ways, to try and make things a little bit more scientific. It means that we can say less when you do that. But I think that saying less is something that we should do more of in our industry. Says the guy who's been waffling on for 30 minutes. But you know what I mean.
Yeah.
We need to be a little bit less convinced, a little bit less rhetoric, and a little bit more sharper scientific definitions of things and how we handle them.
Yeah. It's almost like you're designing your ubiquitous language, Barry.
Potentially, yes, potentially. Although I would warn that that language is fluid and constantly moves, and and eventually always becomes ubiquitous and always becomes meaningless. We'll not get into that kind of philosophy
Yeah,
today, but yes, there's still. I mean, the language will change over time. People are changing the language for me. Um, I've been told off by a lot of people because residuality is a horrendous word to pronounce. Apparently, if you're not an English speaker, it's even worse. Matchas has told me that it sounds like a chemistry textbook, and it's a poor choice of word. But I think it's a better word than leftovers, which made me think of a TV program from about 15 years ago. So.
it makes me think about my fridge.
Yeah, okay. Okay.
All right. So this brings us to the second last question I have for you. So in this podcast, we have a section called Rant Away. You said you started this with rough ideas as at 2019. So it's been 5 years. You mentioned some pushback. So I want to give you the opportunity to rant for 3 minutes about what has been bothering you the most about this journey into introducing this new theory.
So I think the journey started in 2014. It was an internal project for a long time. So it was 2019 before I dared to talk about it on a big stage, or before anyone let me. And I think the thing that's been most disappointing about this journey is that I thought that somewhere up in the sky there were all these thought leaders and gurus, and they all gathered in a big room and had big intelligent discussions about things. And I thought someday they'll let me into that big room. And as time goes on, I'm finding that that big room is just isn't there. So you have to make your own. And one of the things I found is that there is no way for the change in the industry is really, really difficult. It doesn't come from this naive view I had that everyone had a big discussion, decided this is a good idea and there's scientific evidence for it, so let's move forward with it. The industry runs on rhetoric. And once something runs on rhetoric, then there's politics as well. And you can see that bringing a new idea to the industry is dangerous. It's hard work. People will leap on you if you dare to suggest that there's a new idea that's different than their old idea, because they believe very much that they've solved all the world's problems with that old idea. And this slows us down and it scares people away. And it means that people think things but don't dare say because they get swatted down, because there's a general need for consensus. And you can see people won't dare invest in a new idea until they see everyone else do it. And it's very, very difficult to get that last pebble, to get the avalanche sliding. Then once it starts sliding, you can't control it anymore, which is a different problem. But this sort of knee-jerk reflex reaction to new ideas is the one thing that I found most difficult on the entire journey, trying to get people to shift. And what happens is that people will take a new idea and they'll immediately become defensive because it means that their old ideas were possibly harmful to their projects, to their customers, something called the Semmelweis effect. And they will immediately then try to paint their old ideas as the new idea. And so when these ideas in residues are fairly new, very, very new, very, very radical compared to what went before. But I've met people from the Agile movement who said, but we were already doing this. Agile does this. I've met people from enterprise architecture who say, enterprise architecture already does this. I've met people from pop complexity who say, pop complexity already does this. And that's a sign that you're winning, right? That's a sign when you've got all these different fields of thought saying we already thought of this, we already do this. Then that's a sign that you've hit a nerve somewhere. And then you'll ask them, where did you write it down? So, well, we didn't write it down exactly, but it was in a pub in Melbourne in 2014. I said to Jim, and do you remember that, Jim? And Jim's like, no, I was drunk. It gets very, very vague, and so that automatic pushback and almost circling of the wagons when a new idea comes is frustrating, and unnecessary. But it's also natural and human and predicted by people like Thomas Kuhn. Um, You said this is always going to be the reaction to a new idea, especially if you try to shift to a new paradigm, something drastic. It always causes a little bit of panic and that. But the thing that's most irritating is that this is a natural human reaction, but there's no need for all the nastiness that comes with it. That's and sometimes I play on it as well. I mean, I like the idea that the ideas are a little bit thought provoking, a little bit niggling, and sometimes it's nice. And if I see dogma, which our industry suffers from a lot, I like to play with it as well and make it angry, because it just exposes the flaws even more. But it is one of the most difficult things in our industry is getting a new idea, and it leads one to wonder about how many ideas are there in the heads of software engineers and architects out there that don't ever make it out because of these suppression techniques that stop new thinking.
Yeah. All right. So then the podcast is called Satisfying Software. And this is my last question to you. What does it mean when software is satisfying for you?
For me, um, what's really satisfying is when the residues when kick in and you get this effect that the software starts to survive off spec. So building and getting software to run, I mean, that's cool. But the coolest thing is when you come back a year later and they say, this thing happened. Nobody knew it was going to happen. Nobody could have known it was going to happen, but the software still ran. It worked. And I say, yes, that is satisfying. And that's when they say, how did you do that? How did you know that? And that's when we all get to say, we're magic. And that is incredibly satisfying. And what's even better is that so last year I taught so many people residuality theory. I think it was about 600 people. And what's happening now is I'm getting emails from all over the world, and they're saying, we built this thing. They pushed back on us. They said, what are you doing? These ideas are weird. Then this weird thing happened that nobody thought of. The system kept running, and we said, told you so. And I get an incredible amount of satisfaction out of those little stories that keep coming in from all over the world. Because this is what we want to get architecture towards, being able to survive those off-spec things.
All right. Thank you very much for joining us. Good luck with the sales of your second book. We'll put links up so that people can buy it.
Yep.
And I hope to see you soon.
Yep. Thank you. Pleasure.